Hi students, welcome in chemistry classes. I am Priyanka Jain and you are watching videos of thermodynamics. We are studying about the thermodynamic relations. Okay, in our last lectures we have seen Maxwell relationships, non-Maxwell relationships and conversion of coordinates to potential and potential to coordinates. Okay, now we are seeing one of the very important thing, that is equations of state. What is it? Actually, here we are converting the potentials in terms of measurable parameters. It means potential means H, G, U, A. Okay, these are thermodynamic potentials. These values we cannot find out directly. Okay, and actually we want to need them to find out in the terms of the measurable parameters that can be measured directly. And these measurable parameters are pressure, volume and temperature. Okay, so if we find a direct relationship between the potentials and between the measurable parameters, then we can directly find out the potentials. Okay, so this is done here. Actually these are called the equations of state. Actually there are two equations of state. One is that when we are expressing the internal energy. Okay, when the internal energy is expressed in terms of pressure, volume and temperature, this is called the first equation of state. When the internal energy is expressed in the terms of pressure, volume and temperature, this is called first equation of state. And when the enthalpy is expressed in terms of pressure, volume and temperature, then this is called the second equation of state. So actually there are only two equation of states. One is called first equation of state when the internal energy is expressed in the terms of PVT, and second equation of state when the enthalpy is expressed in the terms of PV and T. So first of all we are studying about the first equation of state. First equation of state. Okay, so how we can find out? See here, we know du is equal to TdS minus PdV. Okay, this we know. If we divide it by dV, then what we are getting? We are getting du by dV is equal to TdS upon dV minus P at constant temperature. If the constant temperature we are taking, okay, at the constant temperature, what we can write? Now this d will change by del u. Okay, where we are taking any constant term, then the d is changing by del. So del u upon del v at constant temperature will be equal to T del S upon del V at constant temperature minus P. Okay. Now this will be equation number 1. See here, in this equation we know temperature. Okay, we know pressure, but this is del S upon del V. Entropy actually cannot be directly determined. So we want this equation in the terms of pressure, temperature and volume. So first of all what we have to do? We have to convert this term in the measurable terms. Okay. So it means we want to convert this del S upon del V at constant temperature to any term that is in the terms of pressure, volume and temperature. Okay. So that we can do by the Maxwell relationship. Okay. So see here. First of all make the max bond square SP T V H G A U. Okay, make the arrows. Now you have given del S upon del V at constant temperature. This thing you have given. So this will be equal to del P upon del T. Okay, del P upon del T at constant volume. This is called the Maxwell relationship. This is Maxwell relationship, and I have told you about the Maxwell relationship in our last lectures. Okay, so if you don't know about this, you can see our lecture. Okay, so now we are putting this value in this equation number 1. substituting value in equation 1, what we are getting? We are getting del U upon del V at constant temperature is equal to T del P upon del T at constant V minus P. Okay, this is called the first equation of state. This equation, see here we are taking the U in the terms of pressure, volume and temperature. There is no more terms, only pressure, temperature and volumes that we can determine directly. So this equation is known as the first equation of state. Okay, so remember this equation always. This is very much important equation. This is first equation of state. Now see here, if we are taking an ideal gas, for ideal gas, if we have taken ideal gas, then we know for ideal gas PV is equal to nRT, right? So we can write P will be equal to nRT upon V. Okay. Now if we are differentiating this P, del P upon del T with respect to temperature at constant volume, what we are getting? See here, del upon del T of nRT upon V. Okay, this we are doing. So this nR and V are the constant terms because volume is also constant. So this will come outside. Okay, and del T upon del T will be equal to 1. So this is equal to nR upon V. Now we are substituting this value that we have find out in equation number this. This is equation number 2. This is second equation. This is first equation of the state. So we are substituting this value here. So what we are getting? Del U upon del V at constant temperature is equal to T. Now substitute the value nR upon V minus P. Okay. This will be equal to nRT upon V. Okay. And we know P is equal to nRT upon V. This is written here. So we can write here nRT upon V. So what we are getting? This will be equal to 0. It means for ideal gas at constant temperature, change of the internal energy with respect to volume is equal to 0. Okay. This is the one thing. Now see one more thing. This del U upon del V at constant temperature is also known as the internal pressure. This is called the internal pressure and we denote it by pi T. Okay. So sometimes you will see in the question papers internal pressure. This is called the pi T. Why we are calling it internal pressure? Because it has the units of pressure. This has units of pressure. So this is called the internal pressure. Okay. For ideal gas, this value is equal to 0. It means internal pressure for ideal gas is equal to 0. Actually, this is a measure of intermolecular forces within the system. In the system, whatever the intermolecular forces, this can be determined by this value, internal pressure. Okay. This was for the ideal gas. Suppose we are taking for the Wonderwall gas. Wonderwall gas. If we are taking Wonderwall gas, for Wonderwall gas we know what is the equation? P plus An square upon V square. V minus Nb is equal to nRT. If we are taking 1 mole, for 1 mole, if we are taking 1 mole, what will be our equation? Our equation will be P plus A upon V square, V minus B is equal to RT. Okay. From this equation, what will be the value of pressure? Pressure will be equal to RT upon V minus B minus A upon V square. Okay. So if we want to find out del P upon del T at constant volume, what will be this value? This will be equal to del upon del T of RT upon V minus B minus del upon del T of A upon V square. Okay. Now see here, V is constant. Okay, R is constant and B is also constant. So what we are getting? R upon V minus B del T upon del T. This value will be equal to 1. And secondly, see here, this whole term is constant and there is no T term. So this will be equal to 0. So our value is coming R upon V minus B. Okay, so just put this value. What is our internal pressure? Pi T is equal to del U upon del V at constant temperature. And this value is equal to T del P upon del T at constant V minus P. Just put here the values. Okay, so T into R upon V minus B, and put here the value of P. What is the value of P? P is equal to RT upon V minus B minus A upon V square. Okay. So when you are seeing here, this one is RT upon V minus B and this is also RT upon V minus B. This will cancel out and we are getting this equation A upon V square. So internal pressure for the Wonderwall gases is equal to A upon V square. Okay. Now see the second equation of state. Second equation means when we are expressing the enthalpy in the terms of PV and T. Okay. So for the enthalpy, what is the equation? dH is equal to TdS plus VdP. Okay. Now see here. If we are taking dH upon dP, this will be equal to T ds upon dP plus V. Okay. At constant temperature. We are taking here the constant temperature. So del H upon del P at constant temperature will be equal to T del S upon del P at constant temperature plus volume. Okay. Now here is the term del S. Okay. So we will have to substitute it by the temperature, volume or pressure terms. For this we will use the Maxwell relationships. Okay. So S, P, T and V. H, G, A, U. Okay. Now see here. You have given del S upon del P. It means this term. Del S upon del P. So del S upon del P at constant temperature is equal to del V upon del T. Del V upon del T at constant pressure. Now see here, pressure is at the opposite side of the arrow. So when we are putting here this pressure, then you will have to put here a minus sign. Okay, this is your Maxwell relationship. Now substitute this value in our equation number 1. Okay, so what we are getting? Del H upon del P at constant temperature is equal to T del V upon del T at constant pressure. Put the minus sign here plus V. Okay, this is our another relationship. This is called the second equation of state, because in this equation the enthalpy is now in the terms of pressure, volume and temperature. This is called the second equation of state. Okay, in this equation the term del H upon del P at constant temperature has the units of volume. Now see some questions that has been asked on the basis of the equation of states. Okay. See here this question. Internal pressure pi T of a berth load gas defined as P is equal to nRT upon V minus NV minus AN square upon TV square is equal to. Okay. So we have to find out here the internal pressure. It means del U upon del V at constant temperature. This is called the internal pressure. And for this equation of state is T del P upon del T at constant volume minus P. Okay, so we have given the pressure. We have given the pressure P is equal to nRT upon V minus NB minus AN square upon TV square. Okay, we can find out here del P upon del T at constant volume. For this, del P upon del T at constant volume, we have to find out. del upon del T of nRT upon V minus NV minus del upon del T of an square upon tv square. Okay, so see here, this term is the constant term, n upon v minus nv. This comes outside, and del t upon del t will be equal to 1. So this comes 1 minus here del upon del t of an square upon tv square. See here, an square upon v square is the constant term. Okay, and the differentiation of 1 upon t will be equal to minus 1 upon t square. So this we are getting n upon v minus nv, and this term we are getting an square upon t square v square. Okay, now just put this value in this equation. Equation number 1. In this equation we are putting this value. Okay, so what we are getting, pi t will be equal to del u upon del v at constant temperature. This is equal to T n upon v minus nv plus a n square upon t square v square. Now put here the value of p. What is the value of p? nRT upon v minus nv minus a n square upon tv square. Okay, so in this equation, if you are substituting these values, then what you are getting? You are getting here nRT upon v minus nv plus an square upon v square t minus nRT upon v minus nv plus an square upon tv square. So you can see here, this term and this term will cancel out, and you are getting 2an square upon tv square. So this will be your answer, 2an square upon tv square. This is your answer. Okay, now see the next question. See here, this question is from the paper. What is the question? Internal pressure of dietary gas. We have given pressure value is nRT upon V minus NV, and exponent of minus an upon VRT will be. Okay. In this equation, you will have to find out the internal pressure. Okay. So we know what is the equation. Del U upon del V at constant temperature is equal to T del P upon del T at constant volume minus P. This is called the internal pressure phi T. Okay. For this, we will have to firstly find out the del P upon del T. We will have to find out del P upon del T at constant volume. And we have given what is the value of P. This is the value of P. So just take del upon del T of nRT upon V minus NV exponent of minus an upon VRT. Okay, so what we are getting? We are getting nR upon V minus NV e to power an upon VRT plus nRT upon V minus NV exponent of an upon VRT and then minus an upon RV into minus 1 upon T square. Okay, this will you get by differentiation. Now put this value in this equation. So we are getting del U upon del V at constant temperature is equal to nRT upon V minus NV e to power an upon VRT plus an square upon Vt V minus NV exponent of an upon RTV into T minus, put here the value of the pressure nRT upon V minus NV e to power minus an upon RT. Okay, so by this you are getting what you are getting. You will get this will be equal to an square upon v minus nv e to power an upon rtv. Now you will have to multiply and divide by v minus nv upon nrt. So what you are getting? You will get phi t is equal to an square upon v minus nv into v minus nv upon nrt into nrt upon v minus nv e to power an upon rtv. So this will be equal to anp upon vrt. Okay, this you are getting here. So your answer will be anp upon vrt. Okay. So in this way you will have to do the questions based on the equation of states. Okay. I have done whole the derivation of the equation of states and the questions based on this. Hope you will like this video. If you are liking, please comment me. Please subscribe the channel and please share the video. Thank you.